As humans, throughout history, we've tended to use the inherent structure and materials to our advantage. When my family moved back to Europe, we lived in a place where the soil contained a lot of chalk. Chalky soils can sometimes contain a kind of stone called flint. Flint's an incredibly exciting material if you're a kid or if you're a cave person, and there's quite a lot of overlap there. If you hit a good quality piece of flint with another stone, you can get a very nice ringing noise like a bell. If you hit it harder, you can get pieces to fall off. The process is called conchoidal fracture, and the shape of the piece of flint you get is a result of the direction that shock waves move in the material. These pieces are incredibly sharp, and I mean incredibly sharp. The edge of a piece of flint can be hundreds of times sharper than the best surgeon's scalpel. They can have an edge that's just a few tens of atoms thick and can leave a much cleaner cut than a traditional knife. You can use sharp edges like this to cut through really thin slices of sample, just a few tens of nanometers thick, to look at under the most powerful electron microscopes. Glass knives have long been considered a possible alternative to metal scalpels in surgery because cuts made this way heal up faster and with less scarring. As a kid, learning how to make flint knives and arrowheads was a great way to spend an afternoon, and maybe lose an eye in the process. Out in Norwich in England, there's a place called Grime's Graves, where about 4,500 years ago, Stone Age people discovered large deposits of flint, and they produced one of the world's first industrial landscapes. Thanks to their mining activity, Grime's Graves looks like the surface of the moon. Using deer antlers for pickaxes, they dug up to 14 meters below the ground to get to the flint. To give you an idea of the scale of the operation and the demand for flint, we think that these folks might have brought more than 18,000 tons of flint up to the surface by hand. And that's just based on the number of mine shafts that have been discovered today. At this surface, the flint could have been turned into more than 1 million stone axes. And these axes were exported and sold all across Europe. Remember that we're talking about Neolithic people here. They've only just invented farming, and now it's Amazon Prime for stone tools. In fact, farming was what drove demand for flint tool technology. Even after metal tools were developed, flint was so good and cost-effective that people continued using it for the next 2.5 millennia. I'd argue that improvements in productivity and efficiency, faster farming, and better hunting and gathering was what gave people enough time to sit around inventing Bronze Age technology in the first place. I think that the people who designed and worked the mines figured out how to bring the flint to the surface and then craft it into stone tools were engineers, scientists, and artists in their own right. All this progress, technology, industry, just based on our understanding of how to break up rocks. Now that I've grown up a bit, I've stopped trying to make lethal weapons to throw at my friends, so I work as a scientist. I do research into two-dimensional materials, and these materials have caused something of a revolution in a few different scientific fields. 2D materials can be just a few atoms thick, and there are many that are just a single atom thick. The structure of these materials varies depending on the direction you look in. This is called anisotropy. This anisotropy is really important for making two-dimensional materials, and it's the key to understanding their properties. We usually start with a mineral like graphite, which is a naturally layered structure. Graphite is made of layers and layers of carbon atoms, all joined into sheets called graphene sheets and stacked on top of one another. Graphite's a bit like a deck of playing cards, and now we want to find out if we can take a single card out of the pile. Turns out that we can, which is amazing because this graphene layer is only a single atom thick, and yet you can touch it, move it around, get it to stick across a hole like a soap bubble. What's even more amazing is that this single layer has very different properties to graphite. And that's true of a lot of 2D materials, and there are thousands now. If you take out one, or just a few layers of the material, the properties and behavior of these layers can be rather unexpected. They can be very different from the crystal you started with. It's a bit like if you're a paleontologist and you're splitting open rocks to reveal total surprises. Crack! Look, there's a fern frond inside this one. Crack! Here's a shell. Crack! This process of discovery, the splitting action of the hand and the mind to understand what lies within, is really the heart of what we call analysis. We break problems into smaller pieces so that we can understand them more easily and so that nature can surprise us by revealing its structure. It makes sense that we have to choose how we break the problem apart quite carefully to get the best answer. What's been completely mind-blowing in the field of two-dimensional materials recently is if you really carefully put the layers back together again in a slightly different way, maybe deliberately misaligned, you can make an entirely new material with even more unexpected properties. I don't have a good analogy for this. It doesn't happen in normal life. It's like if we took our fern frond fossil and our shell fossil and we banged them together and a dinosaur jumped out. It's not even entirely true that it's 100% unexpected. Some people actually managed to correctly predict that dinosaur. 2D materials have some really promising applications in electronics, energy storage, and material science. They've been used to make new superconducting systems, fast and efficient transistors, better batteries and supercapacitors, and the potential applications just keep on coming. So while I'd love to talk to you today about 2D materials, the organizers won't let me have the whole day. And to give you a proper idea of what's going on, I'd have to invite hundreds of researchers doing amazing things across many different disciplines. What I do want to give you today is an idea, maybe a new way to look at science and technology. I think some of the technologies that we rely on are set up in opposition to nature, rather than using the best of what's already there. Like the flint, like the graphite. By carefully studying the structure of what nature's already given us, we can really pull in the same direction. But what do I mean by technology in opposition to nature? I mean going against the natural direction, not using diversity and anisotropy to our advantage. Going in the wrong direction usually costs us more energy and has a worse outcome. In one example from my research, we show that if you want to cut up a two-dimensional material, it's a lot easier to do this well along particular directions. In some directions, and with some processes, we can end up with almost atomically smooth edges. And this gives us a real advantage when we want to do something as difficult as pattern materials with atomic precision. Just like splitting up wood, it's much easier to make a straight edge in some directions than in others. We're learning that we have to be very sensitive to the underlying structure of the materials around us to get the best out of them. I think there are a few areas where young engineers and scientists might try to apply a similar thinking. For most of my career, I've been working with carbon, but another of the chemical elements that's really important for us is nitrogen. Nitrogen is the neighbor of carbon on the periodic table, and it makes up about 70% of the air we're breathing right now. Nitrogen in the air is very unreactive because it normally binds chemically with itself. In 2D materials research, we like to say that the bonds between carbon atoms in a layer of graphene are very strong, but the bonds between atoms in nitrogen molecules are nearly twice as strong as those in graphene. As a result, it's really difficult to get nitrogen out of the air and into the chemicals we need. And we need a lot of nitrogen-containing chemicals: fertilizers, explosives, refrigeration agents, plastics, dyes, textiles. The main way we do this is by first making a nitrogen-containing chemical called ammonia, which you may remember from chemistry class in school. The problem is the best way we've found to do this so far is using a process called the Haber process. Now, the Haber process was developed during World War I, so that countries could produce nitrogen-containing compounds without having to rely on the major source of nitrogen compounds at the time, which was guano, bird and bat droppings from Chile. In the Haber process, we combine hydrogen with nitrogen from the air under really high temperature and pressure, 500 degrees Celsius and 200 atmospheres. Remember that nitrogen is really unreactive. We have to use these high temperatures and pressures to make the ammonia. When the process was invented more than 100 years ago, it was a major breakthrough. It was hugely important at the time because, as a species, we were really interested in producing more explosives for World War I. At the time, natural gas seemed to be a cheap and limitless source of energy, and there wasn't much of an understanding about the effect burning so much fossil fuel would have on the environment. The problem that I see is that we're still running this process today. It's estimated that the Haber process consumes up to 2% of the total energy budget of the planet, or about the same as 40,000 coal-fired power stations. The same process results in over 1% of total global greenhouse gas emissions, equivalent to burning about 1 billion barrels of oil every year. There are many ways we might solve this challenge. Some of my colleagues work on designing new catalysts, which are usually anisotropic crystalline materials that can reduce the energy cost of this kind of reaction. This is a really important direction. We could also ask chemists and biologists to look at natural sources. Nature already produces hundreds of billions of tons of nitrogen-containing polymer every year. It's called chitin, and it forms the shells of shellfish and other sea life, exoskeletons of insects, and it's also in fungus and yeast. What's even better is that chitosan, a material closely related to chitin, is an excellent fertilizer, and it was even the world's first biopesticide. It could displace a major use of nitrogen compounds. Artificial fertilizer happens to be what 80% of the Haber process outputs are used for anyway. Chitosan is totally edible and safe, and it's been used in medicine to make wound dressings that help people to heal. Chitosan can even act as a platform compound to produce many chemicals we would normally make from oil. We just need more research to make it happen. What we need to do today is take a good look around us, and I think to reevaluate some of our technologies, to look in the directions we're pulling in, and try to figure out whether we're pulling in the same directions as those found in nature. We might be surprised by what we find. Thank you.
Hi, Tim. Thank you so much for that. That was very interesting.
It was a pleasure.
I had no idea flint was so important.
It's very important.
But I was sitting and thinking about the implications of what you were saying in terms of the stuff that we get out of nature now to help us live and move and develop and progress and all that. And one of the things that I was thinking about was something like fuel, petrol and that, or gas if you're American, all that kind of stuff. Like how do we sort of get over that leap? I mean, obviously the sustainable resources and that kind of thing, but it's happening now, right?
It's a great question. It's a hugely important question, of course, because we've grown up and we use a lot of energy. I mean, throughout most of our history, petrochemicals has been a fantastic and seemingly limitless source of both the base chemicals that we need and energy through burning them.
Yeah.
And it's going to be very difficult to replace that. I think there are a lot of potential options in terms of producing new fuels for the future, much more sustainable ones. For example, there are biofuels based on cellulose and lignins that can replace diesels, and we're looking at bioethanol, which already in many countries performs the role of an additive to maybe 5 or 10% in fuels. So I think more of this looking at natural cycles in nature and figuring out how nature does it, and then providing a cycle to mimic nature in this way will help us achieve those goals. I tend to think, taking the best out of nature still means taking from nature, but we can do it in a bit more of a sensitive way than we have been doing, I think.
Wow. Okay. Thank you so much for that, Tim.